I have a tutorial where we're going to explore Kepler's second law of planetary motion. The first part, we're going to look at the equal area interpretation of Kepler's second law. So equal area and equal time intervals. Kepler's second law of planetary motion states that a line joining a planet and the sun sweeps out equal amounts of area in equal intervals of time. Imagine the situation shown at right in which a planet is moving in a perfectly circular orbit around its companion star. Note that the time between each position is shown is exactly 1 month. Does this planet obey Kepler's second law? How do you know? Alright, so there's our sun and planet orbiting around. Is this planet obeying Kepler's second law? Well, speaking roughly, looks like all of those triangles are the same area. The distance it's moving around, the fraction of that circumference is the same for each one of those months. And so, yes. So equal time intervals have equally spaced locations for the planet. If you were carefully watching this planet during the entire orbit, would the speed of the planet be increasing, decreasing, or staying the same? It's going to be staying the same. So it's going the same distance along this circular path every equal interval of time. So the ratio of distance over the time is the same. So it's neither speeding up nor slowing down. All right. Let's consider another case. In the drawing below, a planet that obeys Kepler's second law is shown at 9 different locations, A through I, during the planet's orbit around its companion star. So A through I. So I'm going to draw 2 lines, one connecting the planet at position A to the star, and a second line connecting the planet at position B to the star, and shade in the area swept out by the planet when traveling from positions A to B. Alright, so let me try to challenge my little art skills here. There's that part and that part. So we're looking at this area. Okay, so think about how big that area is, basically a triangle. Now, pick any 2 positions, C, D, E, F, G, H, I. Note they do not have to be consecutive, that you could use to construct a swept out area that would have approximately the same area as the one you shaded in for question 3. Shade in the second swept out area using the planet's positions that you choose. Note, your shaded area needs to be only roughly the same size. No calculations or quantitative estimates are required. So I think about what the area of that triangle is going to be. Let's say I start from there. Well, so this side of the triangle is actually much shorter than that side. So I must have to go a further way around to get to about the same area as that purple area. I don't know about how much it would be. Let's just say as a guess, it's about that area. That doesn't seem entirely unreasonable. Might be a little bit bigger, probably not smaller. So we'll go with that as being about right. And that's actually going to be sufficient. answer the remaining questions. So, how much time it takes the planet to travel from position to A to position B, how does that time compare to the time it takes to travel between the two positions you selected in question 4, which would be C through F? Well, it's equal areas at equal time, so that has to be equal to. And that's the whole point of Kepler's second law. Sweep out equal areas at equal times. During which of the two time intervals for which you sketch shaded areas in questions 3 and 4 is the distance traveled by the planet greater? Well, A to B, it goes there. C to F goes there. So it's greater for the segment C to F. During which of the two time intervals for which you sketch the shaded areas in questions 3 and 4 would the planet be traveling faster? Well, it's equal time intervals, but I'm going a greater distance. So denominator is the same, but the numerator in the speed is greater from C to F. So it has to be going faster there. If you're going a greater distance in the same time, you have to be moving faster. All right. Part 2, Kepler's second law and the speed of the planets. The drawing below shows another planet's orbit. In this case, the 12 positions shown, A through L, are each exactly 1 month apart. As before, the planet shown obeys Kepler's second law. Does this planet appear to be traveling the same distance each month? Well, my eyes say no, because the distance from F to G is bigger than the distance from A to B. At which position would the planet have been traveling the fastest and the slowest? Position G. And then slowest. Position A. Reasoning. Position G, it's going the largest distance in an equal time interval. Position A, it's going the smallest distance in an equal time interval. At position D, is the speed of the planet increasing or decreasing as time goes on? Let's see, where is D? So at D, the speed of the planet is going to be increasing, right? It's a smaller interval from C to D as from D to E. So the speed of the planet is increasing. Provide a concise statement that describes the relationship that exists between a planet's orbital speed and the planet's distance from its companion star. Okay. So product of distance times speed is constant. So it sweeps out equal areas in equal times. Might be a more artful way of saying that. All right, part 3. Consider eccentricity. Consider the table below listing the orbital eccentricities for objects in the solar system. Recall that an orbit with an eccentricity of 0 is perfectly circular, whereas the highly elliptical orbits shown in parts 1 and 2 would have a high eccentricity of approximately 0.9. And to think about what eccentricity actually is, so here's an ellipse. The semi-major axis is half of the long axis. Semi-minor axis, B, is half of the short axis. And we can construct the eccentricity as, I have the quantity 1 minus semi-minor axis squared over semi-major axis squared, all square root. So if you want to know what that value for Mars's eccentricity of 0.093 actually means, that's telling you something about how close B is to A. If B and A are precisely the same so that this is a circle, I have 1 minus 1, which gives me 0. And if the orbit is a straight line, so B goes to 0, then I have just 1. Because 1 minus 0 is 1, square root of 1 is 1. So the larger the eccentricity, the closer it is to a straight line, and the smaller the eccentricity, closer to 0, the closer the orbit is to a circle. All right, which of the 3 orbits shown below, A, B, or C, would you say most closely matches the shape of Earth's orbit around the sun? Explain your reasoning. So we sort of got the picture that this is about 0.9. For Earth, our eccentricity is 0.016. So B is very close to A for that to be true. So that is probably a good drawing for Earth's orbit. Which of the listed objects would experience the largest change in orbital speed, and which would experience the smallest change in orbital speed? So, which is the most eccentric, and which is the least eccentric? And we go through the largest change. We want the biggest eccentricity, so 0.206. Anything bigger than 0.206? Yes. Pluto, 0.248. So the largest change would be for our friend Pluto. Smallest change is we want to find the smallest eccentricity. So 0.07. Is there anything smaller than 0.07? Neptune's close, 0.08, but still smaller for Venus. So the smallest change, so closest to a constant orbital speed, would be Venus. Describe the extent to which you think Earth's orbital speed changes throughout a year. Explain your reasoning. Well, it's not changing very much. It is nearly circular orbit. Not exactly circular, but pretty close.